So, Ali, we've talked about lots of different designs, features, and so forth, and not to belabor the fact that there are many more features that we've chosen not to talk about, but ultimately, you come to a point that you have to choose a system that you're going to use. I know that you use the ESX system. Can you tell us a little bit about why you use that system, and in particular, the features of that file that make you most comfortable for your choice?
Yeah, I think, I use it specifically for three specific reasons. First is the design features that help me get what I want based on my motion and my usage of the file. I like to design. I like the efficiency that it allows. As a result of thoroughly the protocol that is used for its use and the philosophy behind it, which we're going to talk about in more detail. But let me just mention some of the design features that are specific to this file that make it unique in my usage. For example, the reamer design feature part of it, the fact that it is non-landed, it has a reamer design, so it's triangular in cross-section, it really improves the efficiency and the cutting ability of this file. Now, the alternating contact points is a specific patented design feature that is a part of this file that allows it to do for landed files what lands did. If you recall, we just mentioned that lands were originally implemented so it could keep the file centered in the canal. And if you got rid of the lands, then you would improve the efficiency dramatically, but then you would have issues with transportation and all kinds of other issues. Well, the alternating contact points is the answer. It's a design answer that helps do for the ESX file what lands did for the landed file. Keep it centered, reduce the torque, and reduce the engagement.
So best of both worlds, so to speak.
Yeah.
The issue of efficiency with safety.
Yes, exactly. And the chip space is fairly large, so again, that's another feature of improving its efficiency. It has variable pitch and helical angles that helps it not get sucked down, because that's a problem with some of the files. When they have constant pitch and helical angle, when you put them in the canal, you just get sucked down. It's almost like a screw in effect, and that's something that is not a function of this. And something that's very unique about this file that is only shared with a couple of other files in the entire market is the electropolishing component part of it. Electropolishing is something that manufacturers do as it is a last layer of polishing. And the only two other files in the market that have that electropolishing are, other than the ESX, are the end of sequence as well as the bioerase files. And these files have very, very sharp edges because of this polishing. So it's just one extra step in the processing of the file that gives it that extra quality and improves the efficiency and the strength of the file. And that's why I like it as well. And last but not least is this new feature called the booster tip, which is a tip which we're going to talk about a little bit in more detail, but it helps to keep the file centered. And as a result of this thing, you're able to get rid of a bunch of files in the sequence and end up having the minimal number of files needed for a given canal, which is really a helpful thing. So together, all of these design features help me improve the protocol itself, as well as the design features helps improve the simplicity, the efficiency, and the safety of the system, which is really a key thing. So on the electropolishing front, typically manufacturers, after they grind the nitai, they have to polish it, and they use these normal polishing processes. That still leaves a lot of impurities on the surface of the file.
On the cutting.
And exactly, and potentially
Grinding.
some grain boundaries that could potentially end up, some defects that end up being a
Nucleus for fracture.
Exactly,
Yeah.
a nucleus for fracture and separation of the file. So this electropolishing is basically they take the file and do the reverse process of electroplating. So they basically remove just a very small fraction of the surface, putting it in this cathode and anode bath, and that helps create a surface that is ultimately super polished and yet maintain an edge that is extremely sharp.
How does that translate to when you're using an instrument, that feature? How does it translate to you in terms of your working with the instrument? Do you find it more efficient? Do you find it it cuts easier?
Well, both efficiency and safety. So on the efficiency front, the fact that the edge is sharper helps me cut better. So having a blade, when you're shaving, if you have a blade that is dull, it's gonna irritate your skin. But if you have a sharp blade, then it's going to be greatly helpful. Also, having a surface that's devoid of any imperfections helps reduce that chance of, have you ever take a file right out of the package, you put it in the canal, you just rotate it and just suddenly separates off? Yeah. The traditional polishing leaves those kind of defects that could potentially act as just a defect in the file. It just separates off. So that helps reduce those kinds of defects by doing the electropolishing. Now, the alternating contact points is, the file is created is basically ground in such way that every other cutting edge is ground a 200th of a millimeter smaller, if you will, than what it would be if it were a constant taper, right? But because it's a rotary file, what it happens is that when you rotate it 360 degrees, then you end up getting that constant taper. Mm-hmm. So on the side, it may look like a tiny little bit of a microscopic step appearance, but when you rotate it, you get a constant taper. But what this does is it reduces the torque on the file by 50%. So you have, half the torque that you would be getting if you had a constant tapered file by implementing this patented technology called the alternating contact points. So then the combination of a reamer design, patented, this ACP and electropolishing helps reduce the torque dramatically so that this file can be operated not at the regular 300 RPM that most of the NiTi files are operating it at, but between 500 to 600 RPM. Mm-hmm. And that again increases the efficiency one more time, because at 600 RPM, your file is rotating 10 times per second.
Yep.
So that is, that's a lot. So every second that you're down there, one of these three cutting blades is just kind of scraping off the wall. So it becomes extremely efficient, and that's really an important thing.
Well, early on, I know that the files were originally advocated to be used at around, not these files, but other files just in general, were to be used at around 300 revolutions per minute.
Yeah.
And it was thought that if you increase the revolutions per minute, that you decrease the safety.
Yeah.
But the reality of it is that as you have a more efficient instrument and a more refined instrument, you actually can increase the speed as the result of not needing as much torque in terms of turning the instrument.
Right.
And by doing so, you actually produce finer cutting.
Yeah.
And look at high-speed instrumentation, high-speed
Absolutely.
handpieces versus low-speed.
Right.
Look at the final result.
The key with increasing the speed is to have lighter touch and not stay in there too long, because you're doing a lot more in less time.
Right.
Therefore, that's the reason why you're having a more efficient file.
Right.
So the key is to understand that and not to go down there and stay for extended periods of time. Your time of contact is a fraction of a second to a second. That's all.
Right.
And at that time, you've done 10 revolutions in there. That's plenty enough. So it's basically a very gentle motion of working slowly and and we'll talk about the motion that is required with this file, which is a significant part. But before we do that, I want to talk about booster tip. Okay. So let's take a quick break and come back and talk about what booster tip is.
Okay.